This is the second part of the 3-4 day 2 notes. So you're on the back of that handout. It gives a position function, position as a function of time. It says the position of some body, that just means any mass, any object. At t seconds is represented in meters by that function. Find its acceleration at each time the velocity is 0. So acceleration is the second derivative, velocity is the first derivative. So the first part of this we're going to have to tackle is finding out the times when the velocity is 0. So for velocity, we need the derivative of that position function. So we'll have 3t squared minus 12t plus 9. We're interested when that velocity is 0. This is not a bad one to solve with some factoring. So start to do your factoring on one side. I'd factor out 3. The 3, since it has no variables, could be divided on both sides and will not produce a 0. If you need to stop the video so that you can try this and then come back and compare, that'd be a great way to test yourself. At times of 3 seconds and at times of 1 second would be your zeros of your velocity function. So they're saying the velocity is 0 at times 1 and times 3. They're interested in then what the acceleration is then at each of those points, and acceleration is the second derivative from your time or position time function. Second derivative is going to be 6t minus 12, so I'm just looking back at my initial derivative to get my second derivative. And they're interested at those times, so they're interested in the second derivative's value, the acceleration at 3 seconds, so second derivative's value at 3 seconds. We're looking at 6 now. Here's where the label is going to be interesting. For your derivative, your label would have been meters per second. On your second derivative, your graph for your acceleration would still have seconds as its x label, and it would have meters per second as its y label. So the label on our derivative then is meters per second, or meters per second squared. And some of you have seen that last year when in pre-cal when we did some of those functions where objects were falling, and they were falling at a rate of something in meters per second squared or feet per second squared. So we're going to look at the derivative then of the velocity function at 1 second to find out the acceleration at 1 second. We're looking at -6 meters per second squared there. Remember, do not, if the units are cancelable on the derivative function, don't reduce them because they're representing units from 2 different calculations. All right, in the final part, be sure you can give some reasons for your answer, but stop the video after you get the directions to this part, see if you can come up with these, and then go check, because it will give you that feeling of accomplishment if you say, oh, I totally could do that. So each graph is a separate exercise. Each one shows the position function, the velocity function, which means its derivative, and the acceleration function. So when you're thinking through which is which, we need one graph that represents position with an input of time. That's going to be our position function that most of the time you're calling s of t. We need to find the velocity function. And velocity is also a function of time, because remember our x-axis doesn't change. So that's going to be basically the derivative of so it would look like this, the derivative of the s function with respect to t. And that derivative is going to be then your s prime of t function, your velocity function. And then your acceleration function is also a function of time, which is going to be the derivative of your velocity function. So that's going to be the second derivative. So stop the video at this point. See if for graph number 1 you can identify which is the original position time function, which is the velocity as a function of time, and which is the acceleration as a function of time. Then come back and turn it back on and check graph 1. Okay, so for graph 1, when you take a look at the graph, you've got what looks like a cubic or an odd powered function going here, that one is your position as a function of time. So that one is your S of t function. As you look at that one, you can sort of imagine it's a third powered function or fifth power or something to the like, an odd powered function based on shape, if you're thinking polynomial. But otherwise, when I see it, I see that first of all, the position is gaining, and then decreasing, and then growing again. So when you think about its derivative, the velocity function, it's gonna have to represent the slope of this position time curve. So we're first gonna have to see positive slope, then negative slope, then positive slope in our derivative function. So our derivative function, that first derivative for velocity, is going to be this one. So this is going to be your S prime of t, that parabola looking one. And it makes a little bit of sense. It's something that looked like third power. Its derivative would be something that looked more like second power. So as the velocity is changing, then our acceleration is going to be graphed. So the acceleration is going to have to show, okay, the change in rate of the velocity. So we're looking at slopes, but of the velocity. So in the first part of the velocity function, you're seeing negative slopes for this whole first part of the velocity function from here to here. When you get to here on the velocity function, your slope is 0 at that point, and then you're seeing positive slope. So this is that second derivative, or your acceleration function graph. Be sure that you can give some reasons for your thinking there that talk about the slope and the rate of change. Pause the graph, or pause the video, see if you can do that for graph 2, and then come back. All right, graph 2 is a little bit tougher. This one's the position over time curve. Because of the shape of that, when you look at its slopes to get the velocity curve, this first part of this has negative slope, okay? And then as you continue down, you continue to have negative slopes. So the entire rate of change for that entire function is negative. Therefore, this one is going to be your first derivative, or your velocity function. When you look at your velocity function then, you want to see if you can come up with which one then is your second derivative, or your acceleration function. And you take a look at the slopes here. From here until here, your slopes are negative. At this point somewhere in here, it looks like we have a 0 slope, and then we have positive slope. So this one is your acceleration function. Tonight, you have homework from 3-4 day 2. Be sure to skip number 7 if it wasn't already mentioned. So you have problems 1, 4, 10, 19, 20, and 34. There are 2 graphs on number 10, so make sure that you either have graph paper or make very neat ones. See you tomorrow.